Okay, continuing on with that fascinating, fascinating to me, way in which this radical cation from that we got from the basics of bonding, how is that related to the way in which polyacetylene conducts electricity? So, moving on to the to what I was sharing with you previously was something like this, right? I mean, we said you take a polyacetylene chain, right? You do this fishhook arrow at the very end to give you the diradical. And then we thought the diradical can lose an electron to iodine, which is the oxidant, right? Which is the oxidant, gives you the cation, or cation and a radical, so it's a radical cation at the end of the chain. And instead of now then coupling to give you a CH2 covalent bond iodine, which is what we did here before, the whole thing gets whisked away, right? I was saying that both the plus, the dot and the plus get whisked away from this iodide. So it's delocalized, it's diluted along the chain. So this iodide can never make a bond, covalent bond with the chain. So let's go into that a little bit as to what the hell that sounds like, snake oil salesman, right? I mean, all right, how on earth 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Had something like this. How can this get whisked away? And you had an iodide, right? Ready for bond making here, right? Iodide can be readily made a bond. But then I said, well, you can't do that because this is whisked away. What the hell is that? So first of all, in order to whisk that away, that cannot be whisked away because it's just stuck there, right? Where can it go? This is a CH2, right? I mean, where can it go? So what we can do is this can get whisked away, right? How? There are two electrons, correct? Suppose one were to come here and this one were to come here. What would happen? What would that be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever, 12. Right? Let's call that plus. So if this has come here, so there are two electrons, and then therefore this one has to go here, right? So this double bond breaks. This double bond breaks homolytically, like this one broke before. So what do you think would the product be? So there's no more dot here. This dot and that electron have actually made a double bond here, right? But the dot has moved here. These double bonds are still there. What if this moves here, that moves there, and that moves there? Then what? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? That plus is still there. There's a bond here now. There's a bond here now, but the but the radical has moved here, right? The radical that started here has moved 2 carbons away. So this can go all the way down. So you can what we do is in organic chemistry is we just draw it like this. And then what we do is we take this over here, that over here, that over here, that over here, that to the next chain. So this is how we talk about 4, 6, 8, 10, 12, right? So that remains. So it becomes the whole thing changes flavor. All the double bonds now are, and the dot is here now, right? So now look at what happened. Here, the radical and the cation were next to each other. All of a sudden, you find the radical and the cation as far away from each other as possible. So the electron has moved from this side to this side, right? But you can say, Dr. Manohar, that's great, but the iodide is still here. You can still form the bond here, right? Remember from organic chemistry, when you have a plus next to a double bond, you can have a full arrow, right? 2 arrows mean both electrons are switching, like a windshield wiper. These 2 electrons, windshield wiper on this side. right? So what would be the product? This 1, 2, 4, 6, 8, 10, 12, right? So what happens here? So it's a double bond at the end, right? And because this is windshield wipered here, this becomes positively charged, right? Do you see the arrow formulism here? Sorry, this is not all going this way now. Okay. Do you see the arrow formulism? So the plus charge with iodide is here. It's the plus charge is no longer next to the iodine. It's two carbons away. So let's delve into that, right? Suppose we started off with something like this, right? Let me draw this again. 1, 2, 4, 6, 8, 10, 12, right? So you have this, you have that. And then you have these moving, right? This dot, right? You can still have this, right? This can move here. This can move here. This can move here. Remember, this is double arrows, which means both electrons are moving. So this plus charge can move all the way down the chain. And this kind of dance is what we describe. We can't describe it easily. So we call it like that. That's what I mean by being whisked away. This is the conductive. So the iodide remains here like a long lost soul looking for the plus charge, and the plus charge is completely along all the chains. Okay. So this is what I wanted to mention to you. Important concept, which we have learned here, which I think we've learned it by default. Remember, we talked about CH2 can cleave homolytically to give you CH2 dot, CH2 dot, right? It's a diradical. Remember, there was another thing called heterolytic cleavage, where CH2 can now cleave with a full arrow. When you cleave with the full arrow, go back to the videos, we'll see what happens here. When both the electrons sit on this, you get a CH2 plus and a CH2 minus, right? So similarly, if you have CH2, say, let's call it CH bond, CH bond, CH double bond, CH bond, CH double bond, CH bond, CH. What happens here? Let's say it keeps going. When you do this, what happens? 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4. No, becomes that, right? Keeps going, right? So this is just this, the end of the chain, correct? Now you can see this can move here, killing that positive charge, but creating a new one here, right? But then this can move over here, killing that positive charge, but creating a new one over here. Or this can move over here, creating the positive charge over here. So in the end, you'll have, let's see, 1, 2, 3, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? That's what this is. That's what this is, right? I'm not just writing the CHs, that's all. So this side is still a minus, but this side becomes the plus. And all the double bonds have switched sides, right? So you can have a double bond, a system like this, where the negative charge and the positive charge, the anion and the cation are next to each other. But in a long chain where you have multiple double bonds, the double bonds can dance and whisk away this positive charge from the vicinity of the negative charge all the way to the end of the chain, right? It's another way of looking at it. Okay, so there are two ways arrows can move. One is homolytically, which is this way, which gives you radicals. Radicals means things that have no charge. Or it can move like this to give you a plus and a minus, right? Ions. So reactions that go by this pathway, by the top one, homolytically is called radical pathway. And reactions that take place with full arrows, which you've seen more in organic chemistry, are called ionic pathways, okay? With that, I'll stop this video and then move on to the next stage.